All right. It's a pretty straightforward sort of problem. Basically, of course, if something's compound, then it has more than one element in it. So this sort of problem we're going to do is basically see how much by weight, like if something has carbon, hydrogen, oxygen, what weight percent is carbon, what weight percent is hydrogen, what weight percent is oxygen. That's pretty straightforward. We're going to talk about two types of formulas too. So the first type of problem is a percent elemental composition problem. And so basically you're going to see us take the mass of the element, and it's like a mixture, that's what compounds are, divided by the total mass of the compound, and to get it to percents we're going to multiply by 100%. That's it. That's it. It's pretty straightforward. So it's easier to show you than to describe it. So we're going to come up with a weight percent of carbon, weight percent of hydrogen, weight percent of oxygen brought to the table in this one molecule acetone, given that we have 3 carbons, 6 hydrogens, and 1 oxygen. We're going to actually here in a minute make it a mole basis. So if we have 1 mole cute little acetone molecules, how much mass do we have total, that'll go in the denominator, and then how much mass do we have relatively speaking of the carbon, hydrogen, and oxygen. So we need to knock out the molar mass of acetone. So it'd be 3 times for carbon, decimal number 12.01, plus 6 times 1.008, plus then we finish up for oxygen 1 times 16.00. So 1 mole will weigh 58.08 grams. That's the molar mass of acetone. Then we need to know, then we're going to make as our basis 1 mole of acetone. And then we need to come up with the relative amounts of each element. Well, if our basis is 1 mole of the compound, then with regard to grams brought to the table, in that 58.08 grams, 3 times 12.01 grams is the mass of carbon, 6 times 1.008 grams is the mass of hydrogen, and 1 times 16.00 grams is the mass of oxygen. Of course, these added up all together is equal to 58.08 grams per mole. So on the next page, we just knock out the percentages. So for carbon, we're going to put that 3 times 12.01 grams of carbon divided by 58.08 grams of the compound, C3H6O. To get it parts per 100, multiply by 100 or 100%. And we're going to have to round according to 4 sig figs. So I got weight percent of carbon, 62.04%. For hydrogen, we apply a similar process. There are 6 hydrogens, so we take 6 times 1.008 grams of hydrogen, divided by, again, the same number in the denominator, that 58.08 grams of C3H6O of our compound of interest, times 100 or 100% to get it parts per 100. Round to 4 sig figs, you're looking at 10.41% hydrogen. Now, if you're like, well, I bet I could take 100 and from 100 subtract those 2 quantities to get the last percent, and you're right. But I would suggest you go ahead and just see through and apply in case you made a mistake. So for oxygen, it's 1 times 16.00 grams of oxygen divided by that same number in the denominator, 58.08 grams of C3H6O, to get it to parts per 100 times 100 or 100%. Again, 4 sig figs, and you're looking at 27.55% oxygen. And of course, those should add up to be 100, right? So now, if you're doing a problem like this and you end up with it like 99.95 or 100.05%, that's okay. They should be close to 100. And these actually are directly equal to 100. Okay, so that's percent elemental composition. So we need to kind of differentiate a little bit between the formulas you're used to using, which is probably molecular formulas, and a potentially reduced formula called an empirical formula. So what I like to say is molecular formulas is the real deal. We over here talk about two types of compounds, ionic compounds and molecular compounds. Molecular formulas for sure tell you how many atoms of each type of element there is in that molecule. Now, an empirical formula is the reduced version of a molecular formula, an empirical formula. Now, it's almost easier to show you than to kind of say. But instead of, it will be the lowest whole number ratio of each of the atoms of the different types of elements that are present in that compound, whether it's a molecular or an ionic. So here we go. Let's pick on butane. So the real deal for a butane molecule is 4 carbons and 10 hydrogens. Now we could go ahead and if we divide each by what, 2? By each, I mean divide the number of carbons and the number of hydrogens, then we get 2 carbons and 5 hydrogens. They both have the same relative numbers, but over here in the empirical formula, the C2H5, it's not the real deal, but it is the same relative amounts. Not everything can be reduced. Like water, H2O, you're like, I can't divide 2 and 1 by a whole number and get a reduced set of whole numbers. So in this case, it's molecular formula and its empirical formula the same. Hydrogen peroxide is a good example. It's the same technical as empirical formula. So hydrogen peroxide, one molecule has 2 hydrogens and 2 oxygens. We can divide both of those subscripts by 2 and get 1. So its empirical reduced formula is HO. Hydrazine, N2H4, empirical formula is NH2. These last ones are kind of my favorite. We have a lot of compounds out there that are just what we call hydrocarbons containing hydrogen and carbon. Acetylene is one of them. So the real deal for an acetylene molecule is 2 carbons and 2 hydrogens. Of course, we can reduce that. So that its empirical formula would be C1H1. Well, what about benzene? Benzene is it's a circular molecule, and it's got 6 carbons and 6 hydrogens. So divide 6 and 6 by 6, and you get 1 and 1. So notice that its empirical formula is also CH. So I just think that's neat that we have 2 very different compounds that have different formulas, molecular formulas, and same empirical formula. I'm not sure when we'll get to it in Unit 2, but there's this type of analysis called combustion analysis. And in it, you can take a hydrocarbon and you burn it, and the products will just be water and CO2. So you pick up those masses, and then you end up backtracking from those masses to get the empirical formulas. So that's to say, if we burn acetylene or if we burn benzene, it's going to give us the same empirical formula. And I'm going to tell you here today how you can actually do a little bit more information given, and we can backtrack from that empirical back to the molecular. So that's something to look forward to. Ionic compounds are the crystalline lattice structures. Remember, like we looked at sodium chloride, it had alternating Na plus and Cl minus, Na plus and Cl minus, all in this in its solid state anyway. So generally speaking, ionic compounds are already reduced to their empirical formulas. Okay, so we did a weight percent analysis on acetone. So we came up with the relative weight, the weight percents for the carbon, hydrogen, oxygen. That is kind of That's weight percent, relatively speaking. Empirical formulas with little subscripts give you relative numbers of atoms. So you have relative weight, relative numbers of atoms. So there's definitely a relationship between empirical formulas and weight percents. So the weight percents, percent elemental composition, gives you relative masses. If you have a formula, that's the empirical formula, it gives you relative atoms or numbers of moles of atoms. Okay, so what we did for acetone a minute ago was we took the formula for acetone, little subscripts, 1 mole basis, and took that all the way to relative weights, percent composition. Well, you can also, and I'm going to show you work this problem, go backwards. If somebody says gives you weight, relative weights of each of the elements in a compound, you can go backwards to what is their empirical formula. And then the last little bit we're going to do is take it from its empirical formula with one more piece of information and go to its molecular formula. So let's pick on this compound. So hydrocarbons contain only hydrogen and carbon. And this one is not a hydrocarbon because it also has oxygen in it, quite common. And bottom line, just to tell you what our goal is, you're going to see in the next few slides, is we have something that we know contains carbon, hydrogen, and oxygen, but we don't know the relative numbers of moles. We know weight percent. That's exactly what we're trying to do here. I have 2 problems like this, and I'm going to, when you do problems, if you look at my answer keys, you're going to see I kind of do them different than my slides. I'll do the second problem like I do my homework. In chemistry, oftentimes, we set our bases. And so what we're going to do is not a 1 mole basis like we did before. We're going to say, we got the weight percents. Let's just say we have 100 grams, 100.00 grams, or 100.0 grams of the compound. Now the reason we would do that, and you're going to see this little box up here, is if we have 100 grams of the compound that has carbon, hydrogen, and oxygen, we know from their weight percents that of that 100 grams, 53.3 grams are carbon, 11.2 grams are hydrogen, 35.5 grams are oxygen. So our basis is always to help us. But do you see where I can't put the 53.3 here and the 11.2 here and the 35.5 here because those are relative masses. But I know how to get from masses to moles. And then I could put those there. So let's see what that looks like. All we got to do now is, based on our basis, is take those grams, what we've done before in Unit 1, and get to moles using the molar mass from the periodic table. So let's knock them out. So for carbon, our first term would be 53.3 grams of carbon. We use the periodic table, and for carbon, we've got 1 mole over 12.01 grams, 3 sig figs, so you're looking at 4.44 moles. Okay, so I could put a little subscript 4.44 there. It's not a whole number, so, but we're getting closer. So for hydrogen, based upon its percent hydrogen in 100 grams of sample, you're looking at 11.2 grams of hydrogen, which actually is a lot of hydrogen. Its decimal number or molar mass is 108. Sorry, its molar mass is 1.008 grams of hydrogen per 1 mole of hydrogen. 3 sig figs, you're looking at 11.1 moles. And then last but not least, we take our 35.5 grams of oxygen over 1, use the molar mass of oxygen, which is 16.00 grams of oxygen per 1 mole of oxygen, the flipped version, so our grams will cancel, we're left with moles. 3 sig figs, and you're looking at 2.22 moles. So this actually is sort of getting us down the road. Now we need to kind of scale these so that we have whole numbers. And what you're going to see on the next few slides, and kind of what I'm going to do for the second problem, is that you divide by the smallest number. So the smallest number I got here is 2.22. Okay. And see, did I bring a calculator? Yeah. If we take 11.1 divided by 2.22, oh duh. Well, no, not so duh. We got 5. Okay, so 2.22 divided by 2.22 is 1. 11.1 divided by 2.22 is 5. And I think I can do that one in my head. That's 2. So you're going to have to kind of show me. In fact, I've never shown students like this before. That's the one thing about teaching. You can always change stuff. Like, well, no, I didn't do that. But you're going to have to convey to me all of the steps in on your homework or on your tests. So yeah, we just usually pick the smallest amount. Okay. So if we pick the smallest amount, which was the oxygen, and then kind of saying relative to oxygen, how many carbons, relative to oxygen, how many hydrogens, it looks like this. So yeah, we take the 4.44 divided by 2.22, and we get 2. So we got 2 moles of carbon for every 1 mole of oxygen. And that's exactly what I ended up here. And if we take the 11.1 divided by 2.22, that's where you got 5. So with regard to the oxygen anyway, now I know hydrogen, it's got 5 moles of hydrogen for every 1 mole of oxygen. And so that's where, I mean, this is consistent with this. The second problem we're going to do, and I have a slide coming up that addresses this, is be careful. If these aren't nice whole numbers, it's funny when I do this sort of problem, I'm like a whole number, I'm like, is it a whole number? And it's by dividing by the smallest number of moles I have going in that compound. If it's not a whole number, either you did something wrong, or you're going to have to scale it up, and I'll show you what that looks like. Okay, so the reduced, or the empirical formula, from weight percents, the best you can do is the empirical formula. That's the best you can do. The C2H5O. So this is my warning on if you are working an elemental percent composition to get to the empirical formula and you don't have a whole number, then just be careful. Don't round. I'll show you when you need to go check your numbers. So we got our halvesies going on here. So halvesies is basically you have something 0.5. Okay, something 0.5. So the way this works is, let's say I went ahead and I divided by my lowest number, and I got 1.5 per 1. Well, to get rid of that halvesy, you can see what I've done is you multiply both sides by 2. And if I take 1.5 times 2, I get 3. And if I take 1 times 2, I get 2. So that's the scaling up that I mean. So your subscripts would be these instead of either trying to round up or down. So halvesies are an issue. Thirdsies and 2/3sies are an issue. So if you see something that ends in 0.333 or 0.666, then multiply by 3. So if we take 3 times 1.33, we get 4. And if we take 3 times 1, we get 3. So we're scaling it up. The last one, slide to 0.666s, is the quarters. So if you see a 0.25 or I guess a 0.75 even, we can fix it by taking it times 4. So if we take 4 times 1.25, we get 5. If we take 4 times 1, we get 4. This would be the 3Z's in disguise, the 0.67. Now, if you're like me, I don't know what 2.67 times 3 is right off the top of my head. But by golly, if I have a calculator, I'll take 3 times 2.67 and I'll get 8. But your job when you work these is if after the first pass, if you get a thirds or 2/3 or a quarter or a half, you gotta fix it. You gotta what I call scale. So we're gonna do an example of that. All right. So I'm pretty sure on the homework I did for the OpenStax homework that I furiously did. Goodness, it was not this summer, but the summer before. This is how I would do it. We're going to work another problem, and I'm going to tell you when we divide by our lowest number of moles, it's not going to be a whole number. But what I usually do is set it up in columns. I like columns. So we're going to deal with, I'll start over here so I don't want them. So we have 2 elements, and if you read the problem, our goal is to come up with, from that weight percent, to the empirical formula. Okay. So what I would do is go ahead and make my basis. I would write this on my, basis is 100.0 grams of compound. And then I would go ahead and I would say, based upon their weight percents, I can just put their masses on my little table. 82.7 grams for carbon and 17.3 grams for hydrogen. The other thing about tables is it keeps my stuff organized. So what I did before was to come up with the relative moles. So actually that's what you're going to see here. So I would add my third column, I would say moles, and I would literally, and then this is where, if it's organized in a table, do you see where I don't have to, or even if it has a title here, I don't have to put C because I know it's titled with here or it's in my thing here. So I could just put 82.7 grams over 1 times 1 mole over 12.01 grams for carbon, 3 sig figs, and you're looking at 6.89 moles of carbon because it's in that row. So for hydrogen, you're looking at 17.3 grams of hydrogen. Its decimal number is 1.008 grams of hydrogen for 1 mole, round to 3 sig figs, and you're looking at 17.2 moles. Then what I do is make a 4th column, and I'll title my column divide by the smallest. So I'm going to divide by 6.89 moles. And of course, 6.89 divided by 6.89 is 1.00. And 17.2 divided by 6.89. See, you're looking at 2.50. Right? So that's your halvesies. So then what I would do, and I'm going to show you my slides here in a minute, is I would simply make one more column and I'm going to multiply by 2 to get rid of my halvesies. So 2 times 1.00 of course is 2.00. 2 times 2.50 is 5.00. And then I'm done. So bottom line, carbon, hydrogen. Carbon is 2, hydrogen's 5. That's it. So my slides look like this. It's very similar to this approach. But you divide by the smallest. So if you take that 17.2 moles of hydrogen divided by 6.89 moles of carbon, you get the 2.5 moles of hydrogen for 1 mole of carbon. We want to scale that up. We multiply numerator and denominator by 2. And that's where you get your 5 moles of hydrogen for 2 moles of carbon. It's just, I like the column approach. So I would say, and so your homework, the test that you guys took yesterday, I probably will go ahead and I've done this before, I'll make like a little video and go over it in case you have any questions, and you can watch the video and see how many hits I got in the video, so I know whether I would do it again. But I will say, in general, you guys are communicating very well for your exams, so keep up that good work.
So how can you determine whether you just goofed or whether you need to scale?
You're saying for this first pass, how do you know if you goofed or?
Yeah, like if you come up with some decimal places, like how do you know it's like, oh, I just need to scale it up, or oh, this is wrong? You know what I mean?
I would say if you don't see something clearly, quarters, thirds, or halves, you probably did something wrong. Yeah. Yeah, sad face. What guess? So the empirical formula is C2H5. Okay. So, all we can do is empirical formula. We can't get the molecular formula unless we have another little bit of information. If we have the molar mass of the compound and the empirical formula, and we'll do an example, then you're set to go ahead and go with the molecular mass, the molar mass, and the empirical formula. You can go all the way to the molecular formula. So let's see what that looks like. We'll pick on something that we already knew the empirical formula of from acetone. What is this? No, this isn't acetone. So we know, relatively speaking, we have 2 moles of carbon, 5 moles of hydrogen, 1 mole of oxygen. That's the empirical formula, but we don't know what the molecular formula is. What if somebody said that we know that the molar mass for the compound is 90.1 grams per mole? So what you're going to see done here, well, I'll just do my slides. This is how you do that. So basically, we know we have C2H5O, but we don't know if that's times 1, or we scale it up times 2, which would mean what? C4H10O2, or times 3, do we have C6H15O3? We don't know. We don't know what that X is. So, but we know it's an integer. What we're going to do is come up with the molar mass, that's what MM is, of the repeating unit, the molar mass of the empirical formula. And we're basically going to see how many of those units do we have in the overall, which in this case 90.1. So here we go. So then we're going to take the molar mass of the whole compound, we're going to divide it by the molar mass of the repeating unit, because we're looking for an integer. And hopefully it will be an integer. I don't have a solution for this one. So for the C2H5O1, it looks like this. So 2 times 12.01 plus 5 times 1.008 plus 1 times 16.00. And can you already see that 45 is about half of 90? So that's our repeating unit. So here we go. Then how many repeating units we have is the mass of the whole thing, which was the molar mass of the whole thing, 90.1 grams per mole, divided by the molar mass of the repeating unit. So 90.1 divided by, yeah, I get 1.999556, so that's 2. So that means we have 2 of these units, 2 of the C2H5Os. So the formula then must be C4H10O2. When I say formula, I should have said the molecular formula. So this is the real deal molecular formula, and of course the C2H5O1 was the empirical formula that we were working with. So, you know, I use the word classic, but it's a classic sort of problem. My kids, which are grown now, but they just roll their eyes. Oh, Mom, the classic. Okay. So, homework is due Monday.